Yes, hello together to another session of our statistics course this term. And yeah, we have seen the last time the linear regression, where we introduced some possibility in order to examine a data set, especially if we have two random variables, x and y, and when we have maybe something like this, that we just draw a scatter plot, y and x, and this should be our data points that we started, that we think about how could we, in a good manner, fit a linear line given by y equals a plus bx in order to assume some dependence between these two variables x and y. And there we discussed that it is maybe a good idea in order to calculate always the squared distances of our data point with respect to assumed line, and that we then want to vary, and let me show this. Maybe we assume also such a line is a1 plus b1 x, and then this should be 0, or let's take a third one, which looks like this: y2, a2 plus b2 x. And then we always calculate the squared distances of our data points with respect to different assumed linear lines. And then we want to choose this linear line where choose this linear line for which we have the sum of all squared distances is minimized. Well, and we discussed why we choose the squared distances, and there I said, well, once is that if we choose the square and not the distance itself, we do not have the problem that we have plus minus, so that our data point is below or above our line, so that the distances cannot cancel out. But this we could also obtain if we take just the absolute value. But if we take the absolute value, then especially in the point where we move from minus to plus, where we have this kink, and therefore we have no derivative anymore. And if we don't have a derivative anymore, then you know that in order to calculate an optimum is not that easy anymore, because we cannot take the derivatives at this point. And then we also observed, well, of course, if we take the squared distances, that these squared distances, of course, coincide with our concept of variance, which we developed before. And of course, and this is maybe the most important point, that this squared distance this variance we also observe within the density function of the normal distribution. And since we know due to the central limit theorem that all distributions will take approximately will be approximated by the normal distributions. If we go up in the sample size, then it should be, of course, also a good idea to use the concept of distance which we find in the normal distribution. Well, and this concept, maybe you know it, this comes from maybe the greatest mathematician ever, from Carl Friedrich Gauss, and actually he developed this concept of least squares. Squares was developed by Carl Friedrich Gauss when he measured the distances in northern Germany, because he was asked, by his main donator. This was the Earl in Brunswick, and he said, well, I want to know how large is my land where I'm the Earl of, and therefore he sent out Gauss in order to really measure it in a very significant way. And doing this, he also went by here in the castle of Jever. There was also one point where he measured the distances just in this area here. And since if I'm measuring one point from another point and from a third point, then of course doing this measuring process, I will not end up in the same point, of course. So I have always some error and in order to minimize this error, he invented this concept of least squares. Maybe this also something from the history where it comes from. Okay, but having done this analysis, so calculating this least squares line a plus bxi, then we can also take a step further and asking also how strong is the dependence between our two variables x and y, because of course this linear line can be fitted to every data set. So no matter what your data is looking like, you always can do this least square calculation and you will end up with a linear line. But what you are also interested in, something like how good is my line? Can I really make a forecast that if I have maybe these data points here, y and x, oops, let's take some data point also here, so that maybe this is my best line. And then I maybe want to make a forecast for this number X here. If I increase my money spending in some marketing process, maybe doubling it. And then maybe I found this linear line, and so I can do that. Maybe my revenue is increasing to this point, knowing this linear line. But when I'm doing this, then I want to know how good is my fit to the data. And this question can be answered by the correlation analysis, because of course, in principle, we can calculate for all data sets regression line. And now we want to know how meaningful is this dependence which we found here. How meaningful is this dependence between y and x? And this is done by the so-called Bravais-Pearson correlation index. And this index is then a number which is lying between -1 and 1. And -1 means that we have 100% dependence. If I go up 1 unit in x, then I will go down a specific number b in y. And the other way is known if this correlation coefficient is +1. But how does this correlation coefficient looks like? And for this, we of course also take the known concept of variance, but now we have two variables, x and y. And for this, we have the concept of covariance. I think you also have already heard this in your introductory courses. And this covariance is, of course, very intuitively defined. Remember, the variance was given by the expected value of x minus expected value of x squared. Now we have two variables, so we just multiply the two distances of x and y from the mean of their variables, multiply it, and then taking the expected value. And this, of course, means that the covariance of x is, of course, the variance of x. If we just insert here for y and x, then this is, I think, obvious. So in a very intuitive way, we calculate this covariance. Of course, we don't know this covariance because, again, we have two random variables here. But then we create some data set we are measuring, and when we have measured, then we have our data, and with our data, we can estimate the covariance. Well, and then, of course, we talked about unbiased, about best, about sufficient, and so on, estimators, some probabilities which they should have. And then we also can show that this estimator here is the best unbiased estimator we can find. And remember, again, we have also this factor 1 over n minus 1 in front of the summation that we have found also already as the best estimator for the variance. And of course, this should be the case because, again, if we calculate from this formula here, sigma hat x, so to speak, then this should be, of course, our result which we had some weeks ago. And if you insert just for y here an x, then you see that we obtain the same formula we have already calculated. So this number, this is, again, I thought if I am here in front of it and always pushing on this table that this doesn't happen. Well, it happens still. Again. So, what can we learn from this number? Well, we can learn something from this number, but not enough. And what we can learn is that the greater values of x correspond with the greater values of y, then the covariance should be positive. So we can, from the sign of the covariance, we can interpret that, yeah, so to speak, both variables go in the same direction. So if covariance of xy is larger than 0, then your data set maybe look like this, that intuitively you would fit an increasing line within your data set. And if you have covariance xy is smaller than 0, then of course your data set maybe looked like this, and intuitively you would fit a decreasing line through your data set. But unfortunately, that it was with your covariance. Because, of course, you cannot interpret the number or the absolute value of the covariance in such a way that the higher the value, the more dependent are your variables or something like that. And this, of course, you see that your covariance is just scaling. If you take very large numbers of x, then you could expect that also the covariance will have a greater magnitude. But this, of course, from this you cannot conclude something that your data points are very narrow, scattering very narrow around your fitted line. And for this, then these two guys, Pearson and Bravais, statisticians from just around 100 years ago, they invented the concept of the correlation coefficient, and for this they normalized this covariance, and with this correlation coefficient, then we could show that this can be interpreted as something like the strength of the dependence between these two variables. And how do we, oops, where's my, this is not the right one, didn't I? I have to look it up because I calculated a new slide for you. Let me see if I find it. Oops. So I just stop for a while the